Okay, so let's start then. Yeah, so so let me recall what we did last lecture. So we looked at these generalized Hermite polynomials. In this context, generalized Hermite polynomials. So the kind of context we are going to work is we are interested in this sort of partition functions, which are perturbations of GUV. So this is like we add an extra term, which is like an interaction term, a potential, if you like. So this is integral over Hn exponential of minus t raised of v of h d mu of h. Well, let's not forget, as usual, d mu of h is the Gaussian weight, matrix Gaussian weight. This is again 1 over z0 exponential of minus 1 raised of the squared dh. This b is a polynomial, it's an even polynomial. Where the leading coefficient is positive with positive leading coefficient. So this guarantees that this integral is convergent, because then you will have rapid decay at infinity. And I mean, the case that we study in detail, we simply take v of h or v of x or v of lambda, whatever, to be lambda to the power 4. So this will give us a quartic potential, quartic matrix model. We can put the coefficient later on, but here, whatever coefficient you put here should be positive to make sure that this is convergent. And if this guy is 0, of course, we are back to GOV, which we know a lot of things about it. But this is not solvable easily, but we are trying to solve it by some ingenious techniques, really. Okay, so first of all, there is a Hilbert space L2 of. We look at this now Hilbert space. L2 of R, and the measure that we take here is exponential of it's exponential of minus 1 lambda squared. This is the Gaussian, and then we perturb it negative. Now I want to have a coefficient or not? Yeah, there's a coefficient t over negative t lambda 4 to lambda. Yeah. Actually, maybe I'm going to put v of lambda because a lot of things we are doing works in this generality. And at some point, we are going back to v of lambda equal to lambda 4. Some of the things which is more precise. It's going to be only for that case, but this is the case here. Okay, so then in this context, we introduced generalized Hermite polynomials. So this generalized Hermite polynomial is a system of polynomials P, V, K, K from 0 up to infinity. So these are generalized Hermite polys. And they have the following properties, that P, V, K is monic polynomial of the Vk. Is monic of the Vk. That's one thing. And they have they are orthogonal to each other. Vk, Vl is equal to 0 if K is equal to L. So they're certainly orthogonal. Yeah. So I mean, the first observation is that I mean this exists. The system of polynomials always exists. First of all. Okay, so let me just go. Yeah. So yeah, this thing exists. So first of all, why? Can you give a argument why such a thing exists? Because now this is very general, right? I mean, so, yeah, this is general potential and asking for something. And by the way, this I'm saying is monic of the, yeah, I said of the, yeah, okay. Why such a thing exists?
Is there a way to construct them, I guess, like with the Gram-Schmidt algorithm from other monomials, or
Yes, no, absolutely. Yeah, that's the method. Exactly. So what we'll do, we'll use this inner product, right? So this inner product be denoted by, so the inner product V, or this potential V, is equal to integral. I mean, there is some normalization, but we don't even have to normalize. That's okay. If d bar, that thing exponential of minus 1/2 lambda squared minus TV lambda d lambda. We use this inner product. See, if V is 0, we are back to the Hermite case, the original Hermite case. But this is still a positive definite inner product. And then you can complete space, you get L2 inverse space. And then the argument is exactly as you said. We just use Gram-Schmidt. So we start with monomials 1 lambda squared, lambda cubed, so on. And we apply Gram-Schmidt to this to get this sequence PV. Okay. Okay. Okay, 1, 0. Okay. But we have to use this inner product in the Gram-Schmidt, not the usual logic L2 inner product. If you get this, and normalization is obvious, we can divide by whatever you get, make it monic, and yeah, so that's what it is. So that's for the existence indeed. So one of the things that we notice is that these numbers HK, which are the length of these vectors, PVK, are important. Length squared, norm squared. We denoted that by HK. And then what we did, we looked at this van der Waals determinant, maybe lambda 1, lambda n is equal to this van der Waals determinant. this one. And again, by the same argument that we use for the case of Hermite polynomials, we can apply it in this case as well to show that this is actually, that's a very simple argument. So that this is actually equal to 1, 1, 1, and then, yeah, P, V, 0, lambda, and then P, probably lambda 1, P, V, 0, O. No, P, V, 0 comes first. Yeah. Right. This is P, V, 0, lambda 1, all the way P, V, 0, and then P, V, n minus 1, lambda 1, P, V, n minus 1 of them to lambda n. Because of the properties of determinant, this is exactly equal to n. That's a very important observation. So we also saw that as before, so as in the case of Hermite polynomials, we can apply wide integration formula. Wide integration formula. Implies that actually that integral that we want to study, integral hn exponential of minus t raised of v of h dv of h, because this is an invariant function, it's a unitary invariant function, so we can apply wide integration formula and reduce this integral to eigenvalue space, which is Rn. But this is equal to Cn, some constant Cn, depends on the potential B, of course. Yeah, and then I don't write that step. We just got the formula, which is exactly like the Hermite case. H minus 1, H, Z. Yeah. So now the goal is that we want to calculate these quantities H0, H1, H1 minus 1, because if we can calculate these things, then we can calculate the integral and then take the larger limit. Hopefully, we'll observe some pattern. It's very hard to calculate this thing directly, but we can write a recursion relation. So using recursion, and that's the best that we can do, at least right now. So here's the lemma that tells us how to proceed. The lemma is that indeed lambda pk lambda is equal to p k plus 1 lambda plus k p k minus 1 lambda. So this is an identity between polynomials, and this Rk is a constant, has no lambda dependence. This is a certain constant that we cannot determine now, but we will soon say something very important about Rk. To prove so before I give the proof, I have to make an observation about these Hermite polynomials, is that the way that it goes, actually, you can easily see that, for a k even, p pk is an even function polynomial. For k odd, pk is an odd. So first, note that. So I won't give the proof, but you can find the proof easily. First, note that for k equal to even, respectively odd, PVK of lambda is even, respectively odd polynomial. This is what we have. Okay. Now, how the proof goes now from here. So we are going to just expand, because the space that these guys generate is exactly the space that up to pk generates. So let's write it down. Okay, so first of all, write, then write lambda pk lambda. So this guy is of degree k plus 1, because this is of degree k, and lambda, so degree is increased by 1. So this is of degree k. So we can write it as linear combination of all these things up to degree k plus 1. So we can write it, I just write it as follows. So this can be written as alpha k plus 1 p k plus 1. I dropped v here because it's kind of, yeah, here I already dropped. It's kind of cumbersome to carry v all the time. So I just dropped v here. Okay. So this is this one, and then plus alpha k pk of two lower orders of bit alpha k. Let me see. In fact, they are in R. I mean, it's polynomial or real, but that's okay. Okay, now, first of all, note that alpha k plus 1 is equal to 1 since, so let's observe why alpha k plus 1 is 1. You see, this guy is monic, and this is also monic of degree k plus 1, and the only way for this to be monic of degree k plus 1 is alpha k plus 1 has to be 1, since pk, PIs are monic for all y. Okay. Now, since um, um, now, okay, so now, so I just say alpha k is also equal to 0 by parity. See, if alpha k is not 0, we cannot maintain this parity rule that we have here. If this guy is even, the next one is odd. But if this is not the case, then the next one is going to be to have an opposite parity, and that cannot happen. I mean, same parity actually. So this you can easily convince yourself that alpha k has to be equal to 0 by parity argument. So then, so far we have that lambda pk lambda is equal to pk plus 1, that stays. There is no pk, and then lower order terms. Alpha k minus 1, pk minus 1. And then goes to lower orders. Okay. Yeah. So we can take this subtraction of these things. Lambda pk lambda minus pk plus 1 is equal to this guy. Now, alpha k minus 2, alpha k minus 3, etc., lower orders, are all 0 since, so what is the argument? Yeah, so since lambda pk minus lambda pk plus 1 is orthogonal to pk minus 2, pk minus 3, so on. So if I prove that this quantity here since lambda pk minus pk plus 1, the difference that, so I want to say that actually this difference, yeah, is orthogonal to all these things of degree k minus 2 and k minus 3 and so on.
So sorry, what is that quantity exactly?
Lambda pk? No, not lambda. That's bad. I meant here, this is basically lambda pk minus pk plus 1. This is orthogonal. Thank you. That's better. So we want to show that this is orthogonal. So let's look at the inner product. Okay, now, so the proof of this, the inner product of lambda pk minus pk plus 1. And then, say, let's look at pk minus 2, for example. Let's look at one of them. Okay, so what is this guy? First of all, pk plus 1 and pk minus 2, so I have to use this new inner product D. Yeah, this is orthogonal to that. So that drops from the equation, right? Because this guy is orthogonal. Now it remains to show that this inner product is 0. Lambda pk and pk minus 2. You see, here it's tempting to say that this is 0 because lambda comes out, but no, that's a wrong argument because lambda is a variable, it's not a constant. So we cannot take it out of integral. But we can use the adjoint property. This is equal to lambda times this one. So this is equal to, so let's write it. Here, this is equal to pk and lambda pk minus 2 v, right? pk, because if you look at the inner product, you can just shift it to the other fraction. That's fine. Now, why these guys are 0? Why this guy, for example, is 0? Well, because lambda pk minus 2 is in the span of p0, p1 up to pk. But this is up to pk minus 1, sorry. But this is in pk. And pk is orthogonal to all of them. So this is equal to 0. Same with if you put pk minus 3, pk minus 4, and so on. So obviously, it's also. Okay, so then we just get this equation. Except that here I use alpha k minus 1, but in the statement I use rk, but that's okay. Just one. The end of the argument. So that's kind of tricky argument. Okay, so now we want to find the relation between RK and HK. These constants that come into that equation here. And HK is the length of the electrons. There's a relationship between RK and HK. In fact, the HK is simply the inner product was defined to be PK. V. So we just say this is equal to PK and lambda PK minus 1 V. I mean, yeah, this is should be clear to you. Provide an argument here why this is equal to that. Because when you write lambda pk minus 1, you can write it in terms of pk, which is monic, because this is monic, this is also monic, and then some lower order term. But all lower order inner products are 0. So this gives us the equation. And then I bring it back to the left-hand side, then this is equal to lambda pk, and then pk minus 1. And now I replace by its value for the equation for RK. So this is equal to PK plus 1 plus RK PK minus 1. And then we have PK minus 1. But this is a constant. RK is a constant, unlike lambda. And this inner product by that is 0. So this again drops. I'm only one term limit. This is equal to RK. Inner product of PK minus 1. PK minus 1. V. And this is RK HK minus 1. So yeah, HK, so this is another recursion. HK can be expressed in terms of HK minus 1 with this constant RK. So each time you go up, you multiply by RK. So this is HK, this is HK minus 1. So this is this is kind of funny recursion, but it's not a typical recursion, but these RKs are unknown, but RKs are actually defined by this equation. So what we are going to do now is go back to the partition function and calculate the partition function using the RKs instead of HK. We calculate using HK, now we calculate using RK. Okay, so let's go back to the partition function. Okay, we just use this equation then.
Would HK just be the product of all the RKs?
The product of, sorry?
Oh yeah, of all the RKs, so RK times RK minus 1 times RK minus 2.
Yeah, exactly.
And then R0 is 1 because it's monic. Yeah, so that's
yeah. So that's what it comes from this equation now. So that relation in this here, so let's call this, so HK equal to RK, HK minus 1 is called the star. Now I can say star implies that which is originally equal to that. Now this is equal to C and n factorial. Yeah, R1 to the n minus 1. R2 to n minus 2 times R n minus 1. They're increasing, but then the power of h is just h0 to the power of n. Yeah, h0 is not 1, by the way, right? So, yeah. Okay, so this shows that the partition function can be calculated in terms of R1, R2, so on. And there's only one unknown, which is h0, the length of the first vector. So the next step is to find a recursion for these R's. These are recursion for our case. Yeah, so now there is this integration by part formula. So integration by parts, this is calculus, implies that actually P and Q prime B, so for any two functions actually, it doesn't have to be polynomials, they can be function that are in L2 of the series. B is equal to minus P prime and Q B. Yeah, so it shows that the operation of differentiation is skew adjoint with respect to this inner product as well. Of course, if you want to make it self-adjoint, you have to multiply by I, but that's not what we do. This is skew adjoint. Okay. Oh, no, sorry, it's not. Oh, that's terrible. No. Plus is not actually. I'm very sorry. Inner product P and lambda plus TD prime the derivative of B times Q. B. So this is straightforward to obtain using the definition of this inner product. Because there was that funny perturbed quartic Gaussian, which you just get. That's not the problem. Okay, but the thing is now, I won't repeat it because I will give you the reference actually to read this. There's a very good reference. This equation appears in many sources, but a good reference is this book also I mentioned at the beginning, Londo and Swanky book, Graphs on Surfaces. Londo and Swanky. Graphs on Surfaces. You can read also about this on this derivation, which is it can be shown that actually again you continue this. You need 3-4 more lines, not more. It can be shown that actually we have this equation: K is equal to EK. Oh, sorry, RK. Plus 40 RK. Yeah. Times RK plus 1. Plus RK. Plus RK minus 1. Yeah. So K is just 0, 1, 2, 3, so on runs. So this is a highly nonlinear recursion for Rk plus 1 in terms of Rk and Rk minus 1. So it's a two-term recursion, but it's extremely nonlinear. It's really one of the worst things. It's not easy at all to analyze this recursion because you're dividing this by Rk, and so it's really tough. So this is the Landau is going to call it discrete Van wave 1 equation. Discrete Van We'll meet Van in its full glory, actually, soon, the actual Van equation. But this is a discrete Van equation. Van 1. So these are transcendental functions that are solutions of Van equations. And yeah, actually, this is a discrete version. Yeah. Okay. I believe in physics literature they are called string equations also, but I don't know, not sure. Because now from now on, string theory becomes very irrelevant. Okay, so now the idea of analyzing this hinges on two things. One is this generalized Hermite polynomials. We have come this far. The second portion is to use graphical expansion of this guy. Right. And so next, we need to know the perturbative expansion of this integral of integral over hn exponential of minus e raised of p of h in h. Okay. So this is expansion in two parameters. There's a parameter t, and there's also a parameter n. It's the size of the matrix. We want to know its dependence on both. And and we have to know how fast it grows with respect to t, because we have to rescale. If you don't rescale, you don't get anything. We have to, and we don't know that yet because all we did in the case of matrix integrals was for something much simpler, namely just tracial moments of GUE, right? So let me now write what we did for that, and then we have to expand that method to prove something like a Feynman theorem for this sort of things, which would be the analog of Feynman theorem that we did for usual Gaussian, perturbed Gaussian integrals. A full expansion over graphs. Here we have to do a full expansion over Riemann surfaces, over topological surfaces, not Riemann, but okay, so let me now put you in the context. Okay, as I said, so there are two ideas. One idea is this circle of ideas about Hermite polynomials and so on. And the second is the idea of perturbative expansion. And we put them equal to each other to get information. All right. So that's okay. So recall we calculated again calculated only the zeroth order term the leading term, not the other. We calculated the ratio of moments. Race of H to M, right? This was GUE. This was by definition equal to 1 over Z integral race of H to M. Yeah, d mu of H over Hn over the space of all Hermitian matrices. So yeah, and we wrote an expansion in terms of powers of n, which is genus expansion. Some Riemann surfaces up to some genus appear, not more than that, depending on n. And how we did that? So we used a direct approach to this is rather difficult, but we used a trick, a graphical device, which is polygon gluing. So, and this was like a magic. So we used the polygon gluings. Of course, plus Fick's theorem. So what we did, we proved that this guy, race of H to M is equal to some n to the power V of sigma over this is capital N over sigma, where sigma is a pairing or gluing of a 2M gun with sigma belonging to pairing or gluing of a 2M gun, right? This is what we observed using Fick's theorem. And then what we did, so what is this gluing? Here is a 6 gun, for example. So we just chose one gluing like this. And then this gave us one term into this expansion. And then we used the Euler's formula, right? So the Euler, so we obtain a surface, closed surface. Also a surface sigma. We obtain a closed oriented surface sigma. And then the thing is, Euler characteristic of this sigma is actually equal to number of vertices minus edges plus spaces. But in this case, in all these polygon gluings, there's always one face. These are called one face maps. And number of vertices, well, we have to keep it, we don't know. And then minus edges. The edge is always known because it's half of the edges here because we are paving. It's only m remains plus 1. But this is, of course, 2 minus 2g, right? So here you get that V of sigma. If you bring it to this side, you get is equal to m plus 1 minus 2g. Right, get m plus 1 minus 2. So alternatively, then we can write this not in terms of vertices, but in terms of genus of the Riemann of the surface that we obtain. Right? So the formula in terms of genus is this formula. Genus that we get race of h to n is equal to that n to the power n plus 1 some epsilon g n over n to the power 2g. So this expression, right? This expression here can be equally written as such, where epsilon gn is number of different ways that you can glue a surface of genus G from a pairing sigma. The number of ways to obtain a surface of genus G from a pairing. Okay, so yeah, and then what we observed is that the planar terms, the leading term, G equal to 0. In physics, they'll call it planar because they correspond to a sphere, and a sphere is flat if you punch one point on the sphere. G equal to 0, planar. Is epsilon 0 m. Do you remember what that number was? It's a Catalan number. Exactly, it's a Catalan number, and this is exactly the case where you have non-crossing pairings, right? Is equal to Cm, which is also equal to number of non-crossing pairings or gluings of a lambda. Yeah, but then any knowledge of epsilon 1, epsilon 2, higher genus 1 is extremely difficult, man. This is the subject of Harazagi's theorem, which I only stated, but this, and of course, from this we can derive, we derive the fact, the Wigner's semicircular and all that. Okay. But notice that this is only a kind of baby version of what we want. We want now to write this thing. We want to find a perturbative expansion of this thing. And this can be done using this method, because if we just bring it down using the formula for exponential and bring it down, we can write the sum of powers again, reduce it to this term, and to sums of those terms. But there is a method that was, this is not the method that was originally used. The method that was originally used is by Tooft, which is called summing over fat graphs or ribbon graphs. So I will mention that now. I'll take 5 minutes and then. Okay, so yeah, so now summing over ribbon graphs. There's another name for it. is also path graphs. But these are in reality closed, not closed. These are surfaces with boundary, oriented surfaces with boundary. So this is equal to oriented surfaces with boundaries now. So it's a different kind of topological object, closely related to that, but not quite the same. And the way we obtain it is also different. So what is a ribbon graph? Basically, imagine you have a vertex, right? Which we met these vertices like that in expansion of Feynman integrals in one variable case, so not over matrices, but over functions. So what we're going to do? So we're going to create a. I mean, basically, we can also go back and forth. We're going to create a ribbon graph based on this as follows. So we just say, okay. So you can imagine there is this still original vertex there, but just. And we're going to, okay, so this is like a trivalent ribbon. So, I mean, it's not matched yet, but this is a trivalent. You can have 4 vertex. Again, you can, yeah, you can actually write the corresponding, I mean, draw the corresponding 4-valent thing. Okay. Now we orient these things with counterclockwise orientation, each of these guys. Actually, I'm giving it clockwise orientation. Where I go. I have to make sure, am I using counterclockwise or clockwise? Actually, clockwise orientation. So I just go like this. Here is just ij, jk, kl, li. You just put indices like that for now. And in this case, I put ij, jk, ki, etc. Now, how we are going to glue these things? Because the thing is, to get a ribbon graph, we have to close these semi ribbons. These are kind of bunch of semi ribbons. How we are going to glue it? Gluing is dictated by this thing, by Wick's lemma. So let me now write. So Wick's theorem, as we use also over there. So now imagine we want to compute something like this. I want to compute trace of H4, right? So this is equal to sum. If you just expand H4, trace of H4 is just Ij, right? Hij, Hjk, Hkr, Hl. So now, a priori, I, J, K, L go from 1 to n. So there are n to the power 4 choice of indices. However, we know that that we have this sort of kind of relations for propagators that Hij, Hkl is just equal to H Okay, so let me write it like this, delta IL, delta JK, right? Okay, so let's have this in mind, but let's continue here. So this is the big step, right? Big tells me that this is sum of three sums. One is actually sum Hij, Hjk times HKL, HLR plus, and then I get first and last, I mean, so Hij, HLI, right, times HJK, HKL. I mean, this sum is applied to all of them, so it's IJKL plus the crossing term now, which is Hij, HKL, HJK, HJK, HLR. And I closed it. Right? So this is what Wix tells us. Now, this relation, of course, tells us that here there is only one condition, which is I has to be equal to K. There's no the other variables are free. You can choose anything. So here I has to be equal to K. So you get the sum of n cubed, right? In this case. Here also, the only condition because of this is that non-zero terms correspond to I equal to V in this case, J equal to L. And then you get a Q. But in this case, you have more conditions because J has to be equal to K, I has to be equal to L, and so on. J has to be equal to K, I has to be equal to L, and K has to be equal to L as well. Yeah. So then you get N. Yeah. Okay. So if you wanted to do this here, so let's look at this 4 vertex. So there are 3 different gluings of the 4 vertex now. Okay. So I'm going to finish now. So 3 different gluing of the 4 vertex. I mean 4 valent, not 4 valent. Did I say 4? Yeah, 4 valent. So let me draw this now. So here is 1. So let's not forget about this indices, Ij, Jk, Kl, Li. So you can glue these two, and these two. So you get this one now, right? And then here, so get this. So this is a closed ribbon that we get, right? Now, this contributes to something non-zero in this case. But now let us look at this index 3 here. This tree is exactly the number of boundaries of it. Okay. So P is equal to number of boundaries of, so let's call this ribbon now gamma. The number of boundaries of gamma. Z class.
Actually, today I think it was only till 230.
Oh.
Today it was only till 230, the class.
Oh yeah. If
The
you want
Monday
to check
class.
if there is someone. Maybe I have to. That was just random checking. Okay, so it's the number of this one. Okay. And in this case, you also this term corresponds to the other gluing. Now this time we can just do this. Again, you get 3 boundaries for this case. So this contributes n cubed, this contributes n cubed. And then, but then there is one more case that we can do gluing here, which is the following. So let me just write it down. So let me just draw it here. So I can bring these things here, glue like that. And then this has to go under or above. We get this. Now remember, this ribbon cannot be drawn on a sphere because of this crossing. But this can be drawn on a torus. In fact, the thing is a torus. But also notice that there's only one bound. So it's one bound. So one boundary. So if you look at this thing, so this term, by using just graphs, then I can just write, I give n to the power 1, which is n to the power the number of boundaries of this guy. But now you notice that if you draw this on a surface, the number of boundaries is equal to number of faces that number of faces. So I'm going to stick to this case number of faces. So this is now essentially Hooft's observation that he called it double lines, because in the case of Feynman thing, it was one line. Propagators were sitting on the one line, but in this case, because matrix has 2 indices, we have double lines. And the gluings produce this sort of different things. But you don't get anything different in this case. You get exactly the same formula that we had previously. So when we come back, I'll generalize this to the case of quartic matrix integral. We write the full expansion, and that's a bit more general. But again, is in terms of summing over topological surfaces, and that's the full genus surface, genus expansion that we need. And then from there, we go to continue. We put the 2 things together. Okay, thank you for your patience. So I went over time. Are there any questions in the Zoom?
Oh, I was wondering if we would get even powers if we looked at the non-orientable surfaces. So with the twist,
Oh,
but then
yeah,
we'd have to change the inner product of the HIJs so that you can make a twist, I
yeah.
guess.
Yeah, there's a twist in that case, and I'm afraid working over, for example, symmetric matrices, you have to go to that case actually. Yeah, I I never looked at real symmetric matrices, I should say.
Ah, true. Oh yeah, it works for the real symmetric one. That's right.
Yeah, real symmetry is much more complicated actually.
It's true.
I mean, the complex word is much simpler despite its naming. That's kind of funny, but that's what it is. I mean, it's like a really ideal world for to be in. The real world is much more complicated, much more complex. Yeah, that's what it is. Yeah. Okay, but again, in Zwankin, you will get something about this as well, Zwankin Lando. But there are many sources. I think the book of Einard also considers the symmetric case as well, a little bit at least. But yeah. Okay, excellent. So looks like there are no other questions. Thank you very much. I'll just say goodbye and we'll just see you on Wednesday.